Good morning, everybody. Thank you for coming and welcome to Tyrone-Intel oneAPI live webinar series. I will be introducing our speakers for today. Sandip Sir, Director of NetWeb, and Vinita, a Technical Consultant Engineer from Intel. Please note that we will not be taking any questions through voice chat. Please leave your questions in the Q&A section. If you see, it's the other tab in the chat, and then we will answer your questions later in the end of the presentation when we have a Q&A session then. Okay. Sandeep sir, you can start.
Welcome everybody for this webinar. I am Sandeep Lodha from NetWeb, and I will be giving you a brief introduction about NetWeb and also some of the products and solutions from NetWeb, which might be of great interest to you. So to give you an idea about NetWeb is that we have got presence in about 5 countries today. We have got thousands of customers. On the HPC side, we do have 500 or more installations. We do have a large deployments of the GPU cloud solutions all across, and we have been doing a lot of work on big data, AI, and things like that. We do have integration units, about 3 or 4 of the integration units across in Singapore, Indonesia, and India. We have been doing some top edge computing and products and solutions from our side. So talking about the global presence, as I have already mentioned you, these are our units which are there, and we do have a manufacturing and R&D center in India, Faridabad. So coming to the solutions, we do have a huge range of solutions starting from data center computing. We do have more than 500 different servers and solutions to pick up from. We do have storage solutions which are for enterprise grade solutions like unified storage, where you can have a NAS, SAN, and virtual tape library in one box, and you can also connect to any kind of a network, starting from gigabit Ethernet to InfiniBand to fiber channel and more. We do have SAF-based storage solutions. We have got special storage solutions for surveillance and archival, and we do have a PFS solution based on Lustre. HPC, we have been doing a lot, and we have been into all kind of different kind of HPC solutions. We do have our own management tool, which I would be speaking about in some details. We have been doing a lot of cloud installations, maybe it is public or private or a hybrid cloud, and we have been doing a lot of hyperconverged solutions also regarding this. We have been doing a lot of projects on the big data AI, where we also have a data science team which does those kind of development for you. On the containers, we do have some excellent products, and we do have some containerized solution platforms which we support for our HPC and AI customers all across. So these are our engineered solutions basically. So we do have a Tyrone container platform. We do have Tyrone Kubites, which is a repository. Then we have got Skylus, which is a hyper-converged solution, which has got compute and storage both. And it is a very, very fast way to having a private cloud on premises. We also have Tyrone Cloud Suite for a large HPC installations, cloud installations. We have all our products have been helped by our customers seeing their pain points, and we take them to our innovation center. We try to solve those problems out for you, and this is how we develop those products and solutions which you can further use. And we have been getting amazing feedbacks of the products and solutions which are coming from our innovation labs. So we are also into a lot of services, HPC being one, of course, AI labs, as I mentioned to you, any backup disaster recovery, cloud migration, data center related services, and things like that. Talking about Tyrone Cluster Manager, this is our HPC deployment tool. So basically what it does is very fast deployment of your HPC, provisioning of your nodes, monitoring them, also monitoring your queue systems and other things, and also repositioning it as you go forward. So this makes the entire cluster very easy to handle. And we do have this software which has been we have been selling it to the customers, as well as a lot of our customers who are using our HPC are using TCM for all their operations. Coming down to a qubit ecosystem which we do have. So explaining this is that today we do have this GPUs, CPUs, FPGAs, and edge computing related processors and things like that. We do have the software ecosystem where we also do have oneAPI and things like that. We do have Cafe, PyTorch, Theano, and TensorFlow and other stuff. So what happens is the deployment to the hardware with these frameworks, we require an ecosystem where we require the containers and the VMs, and we handle all this through qubits, TCM, and Tyrone Container Platform. So this makes your accelerated growth and deployment of these applications, and this is a very, very necessary part of the ecosystem going forward. And we have got a lot of products and solutions which fills in the gap for this particular ecosystem. So what is Tyrone qubits basically? So it's a repository basically. It is a repository not only for GPU, it is also for the CPU, and coming forth we will be having many more other repository and every different kind of things. We handle two types of applications right now, which is HPC and AI. And we also have various kinds of containers, basically. So there are some containers which can really scale very high across many nodes and still give you a bare metal performances. You can run many of these applications, so you can do a very optimal utilization of your resources, whichever you have got. So this gives a big flexibility to our customers. So talking about it, as I already mentioned, that we support CPU, GPU, FPGA, and other accelerated solutions. The idea is that your deployment should be very, very fast, and it comes with our Tyrone AI expert, which gives you the immediate support and things required. We also do undertake, suppose you do have a kind of a container requirement to be made, and we can do the customized container deployment for you. And what we can, suppose you've got an AI related application and you want to make a container so that the deployment at the edge or various locations can be at ease, we can do all of those. We have already adding a lot of HPC related containers in our repository, and you will soon have a very bare metal performances out of those containers with complete control on the user side, and it will give you a real good performances. So just talking about, we do have a qubit certified hardware, and we are talking to many vendors also to have the qubit certification on the hardware. Right now, the workstations are already coming with qubit certification. And the idea is that from the qubit cloud, you can just pull up any kind of application and it gets installed in seconds, and you get the bare metal performances, which are very high. So we have got more than 50 containerized applications and more than hundreds of containers already in our repository. Right. So sorry. Yeah. So these are few of our customers. We have got a huge range of customers on HPC. We have been doing a lot of deployments in the cloud. We have done a large companies where we have provided big data and AI solutions. On the data center side and the storage side, we do have again a very impressive list of customers who have been using our products and solutions. Right. So this is all from me, and I would now like to go back to Vinuta who is going to actually give you the main topic of the webinar today, would be covered by her. Thank you so much, and we'll meet at the end for the uh, 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 we'll meet at the end for the Q&A section. Thank you so much.
Software profiling tools from Intel, which are Advisor and Intel VTune Profiler. These are part of our oneAPI based toolkit. And this in the next 1 hour, we will try to understand how we can profile a GPU application using these tools, and also try to understand how these tools can help us to unleash the performance bottlenecks of your application. Okay, so this is the brief agenda that I will be covering in the next 1 hour. We will talk about Intel Advisor. We will also learn about what Offload Advisor is, what GPU Roofline analysis is all about, and two important features from Intel VTune Profiler that helps in GPU profiling, which are GPU offload analysis and GPU compute or media hotspot analysis. And then at the end, we will wrap it up with a summary. Okay, so let's get started. Intel Advisor. Intel Advisor is one of the profiling tools which is present from quite some time. I'm not sure how many of you are aware of it, but it is one of the profiling tools which is mainly used to improve the vectorization and threading aspects of your application, which means that using Intel Advisor, you will unblock vectorization opportunities in your application, and also it will help you to unblock the threading inefficiency in your applications. So this is the traditional advisor, and with Intel oneAPI, there are two new features of the capabilities that have been added to Intel Advisor, which are offload modeling and the GPU roofline analysis. I will talk more about what roofline analysis is all about in detail in the next few slides. But just to give you a high-level overview of what Intel Advisor is all about, this was initially it was mainly to unblock vectorization and threading inefficiencies in your application. But with Intel oneAPI, the two new features, offload modeling and the GPU roofline analysis features or the capabilities have been added. Okay. So, as I said earlier, offload modeling or the offload advisor is the new capability that has been added to Intel Advisor from Intel oneAPI onwards. And what offload advisor is all about, we will talk about that. So, offload advisor is one of the feature that helps you identify the potential candidates in your application which can be offloaded to GPU, and it will also help you to identify what is the potential speed up going to be by offloading certain region onto the GPU. And it will also help you to identify the data transfer estimations if there are any potential bottlenecks in your application which can be fixed and make your application GPU ready, right? So if you aren't aware of what advisor is actually capable of doing, I'm just gonna give just high level overview of it. So advisor actually has a set of several analysis types like survey analysis, dependency analysis, strip count and flop analysis, and memory access pattern analysis. So all these different types of analysis are still supported when I say offload advisor, but the one extra thing that is supported is offload modeling. So which means that if we are going to run these different types of analysis that are supported by advisor, and offload modeling is going to perform an offload modeling on a given architecture. or a given accelerator. Currently, only the Intel GPU is supported. So, offload modeling can model for currently Gen 9 and Gen 11 GPU cards, Intel GPU cards. When we run Offload Advisor, we will, at the end of the analysis, we will be getting a HTML report, which would look something like this. And in the next few slides, I will talk about in detail how to interpret this particular report that we get from Offload Advisor. So to conclude this slide, Offload Advisor is mainly to identify the potential candidates in your application, which can be offloaded to GPU, and you will also get a potential performance speed up by offloading the particular piece of a section to the target platform, which is a GPU. Okay. So as I said earlier, at the end of Offload Advisor analysis, you will be getting a HTML report, and and you will be landing with a summary page which gives some high-level important metrics of your application, and I'm going to cover some of them in next few slides. So here, what you see in the summary page is this. Initially, you will be seeing speed up of the accelerated code. So which means that potential speed up that you will get by offloading the certain piece of code that Offload Advisor has identified, which has to be offloaded to the target platform, which is a GPU. And next, you will get to see the program metrics. So here we will see the different timing data, which is the original timing and the accelerated timing. Original timing is nothing but the total timing of your application, which is running on a CPU or a host device. And accelerated timing is nothing but the total timing of your application where it is running on host, as well as some portion of your application which has been offloaded to the GPU is running on the GPU or a target device. So this accelerated timing is CPU plus GPU time. Original timing is only the CPU time. Okay, and then the target platform, which is Gen 9 GT2 here. So which means that when we run Offload Advisor, we will have to specify for which target platform or which target accelerator you want the modeling to be done for. So in this case, I have given Intel Gen 9 architecture as a target platform. So it has modeled the report for Gen 9 architecture. Similarly, I can specify for Gen 11 if I want to model it for Gen 11 and upcoming Intel discrete GPUs as well. So next, coming to number of offloads, so which means that there is one offload section that it has identified, and then speed up of the accelerated code. So this is the total speed up of the accelerated code, which means that if you divide the original timing with the time on accelerator, so time on accelerator is nothing but how much of time it is running on accelerator on the GPU. So when I say if you look at this 1.63 second, which is the accelerated timing, this is nothing but addition of these two timings, which means that how much time it is out of 1.63 seconds, 0.09 seconds it is running on host, and 1.54 seconds it is running on GPU. Okay, so speed of accelerated code is nothing but when you divide this original timing with the time on accelerators, you get that. And you all know what Amdahl's law is. So whatever the speed up that you achieve, it actually going to be dependent on the serial code that it is that it is running. So this will be original timing to the accelerated timing. So that means some of your application will still be running on CPU and some will be running on GPU. So the speed up that you get based on Amdahl's law will be original by the accelerated timing. And then you will also get to see some other timings related to data transfer, invocation tags, code transfer, and all. So this is good to know. Whenever you see more timing here in the data transfer, which means that you are going to spend a lot of time in data transfer, that is the caution, and you will have to probably look into those stuffs in detail. Okay, in the summary page, apart from these program metrics and the potential, the speed up, you will also get to see other different metrics like offloads bounded by. So what is that your workload is bounded by? Is it bounded by compute or a bandwidth or a memory or the data transfer and so on? And you will also see top offloaded section, which means that it's again, it's all since it's in from the summary page, this is all high level. You will get in details in the next few tabs of the report. So at high level, it will show what is that the section of the code that the offload advisor has identified, which can be offloaded to the GPU, and which is a beneficial to offload it to GPU. And you will also see like CPU and GPU timings, and what is the gain and what it is bounded by. So currently, this particular loop that has been identified as a potential candidate is bounded by the LLC bandwidth. So the top offloaded will have all the potential candidates that can be offloaded to GPU. And if we will also have the top non-offloaded section, which means that these are the candidates that are not so good to offload to the GPU. So you should restrain yourself from considering these sections for the GPU offload. So the reasons could be many. It has identified this cannot be offloaded because it might have some dependencies, or the total time is or iterations are too small. It couldn't model, or total time itself is so small, and you will not get any benefit by running it onto the GPU. So from the summary section, what you can take out is that what is the speed up is going to be, what is that my workload is going to be bounded by, and what is the top offload regions that the offload advisor has identified, and what are the top non-offloadable regions that it has identified. So these are the few things that we can take out from the summary page once you finish running offload advisor. Okay, so here is some more details on this offload bounded by section. So usually our application performance will ultimately have some upper bound based on some hardware limitations, right? So there are several limitations that the offload advisor can indicate, but they generally come down to either compute or memory or the LLC bandwidth and so on. So knowing what your application is bounded becomes very critical in developing an optimization strategy. So this is also one of the metric that we will have to look for when we get offload advisor report. Okay, so earlier I said it was all summary. So if you see here in this, you do see this summary tab. So it had all those details, high level metrics of the offload advisor report. Next to that, you have a few other tabs like offloaded regions, non-offloaded regions, call tree, configuration logs, etc. So when I click on offloaded regions tab, so this is where I'll get some detailed analysis report of the potential region that the offload advisor has identified to be offloaded to GPU. So once you click on this, you will get to see on the right hand side, you will get to see the source. So it highlights what part of the code can be offloaded to GPU, either by using DPC++ or OpenMP. Okay, and you here on the left hand side, you will also have several metrics related to timing. What is the timing that it is taking currently on CPU, how much it is going to be when it runs on GPU, and then offload metrics like offload taxes, data transfer taxes, or how much of the memory that is being transferred to and from the CPU to GPU, GPU back to the CPU, and so on. So this becomes somewhat important when you have to go and offload this particular section. You will have to go and look at all these metrics and understand if how much of if there is any data transfer overhead or the invocation tax or kernel or any other taxes that would come in between. Okay. So, as I said earlier, we will have to keep an eye on data transfer taxes, because as you put your application to discrete GPUs, it is important to consider how much of your data will be transferred from your CPU to GPU and also back to your CPU. So, this data transfer cost can often decide if GPU offload is worth. So, it is always important to have a look at the data transfer metrics that the Offload Advisor provides. So if you see in this picture, you see that it's around 24 MB of data is being transferred. It also tells you what is it, a memory object which is causing this data transfer, how much of memory has been transferred, is it transferred from CPU to GPU or GPU to CPU. All those details related to data transfer we will get to know from this. So to conclude this, you will have once you have a detailed look at your offloaded regions report, please pay attention to the data transfer metrics as well, because it is important factor which can decide if the offload is going to be worth or not. Okay, similar to offloaded regions, there is also a non-offloaded regions section or a tab. So this actually captures all the different non-offloadable regions that it has identified, along with with the reasons why it cannot be offloaded. Like for in some cases, in some loops, there might be a dependency issue. So it decides that if it cannot be executed in parallel, it's of no use to running on GPU. So it's not profitable to upload it to GPU, or as I said earlier, timing might be, or a number of iterations might be very less. So it's like it's taking very less time on CPU itself. So it may not be profitable if you port it to GPU. So you will get what are the sections or the loops that you should not be offloading to GPU, along with the reasons why it cannot be offloaded to GPU. Okay, so again, all this reports, whatever that we see from Offload Advisor, they're all application dependent, workload dependent, and also sometimes platform dependent. So for some application, for an application with certain workload, when you run Offload Advisor, you may not see any offloadable candidates at all. So you will not see any speed up for accelerated code at all, which means that it hasn't identified any offload regions at all. But for the same application with another different workload, it may be able to identify the offload regions, and it may be able to come up with the speed up also. So and also as it's a platform dependent, which means that when I run a certain application with certain workload on Gen 9 architecture, it may not be able to get you any offloadable regions, or it will not be able to show any speed up. But at the same time, if you, let's say, if you run the similar application and workload on Gen 11, because Gen 9 and Gen 11 architectures are again different architectures, the Offload Advisor may identify some of the offloadable regions, and also it will be able to come up with the speed up for the target platform. So what I'm trying to say here is that these reports are all application dependent, workload dependent, and also platform dependent. For some application and some workload, you may not be able to see the benefit of offloading to GPU, but for some other workload or some other platform, you may be able to get a potential speed up by offloading to a GPU. Okay, so this is just one slide on how you can run Offload Advisor or Intel Advisor. If you are a GUI user, there is a very nice GUI available from where you can run Intel Advisor and also Offload Advisor. If you are a non-GUI user, there is the command line utility which is very well supported, and there is also we have recently added Python scripts to help users to get started with easily. So you don't have to go and dig on what exact command line that you have to use and all those things. So these are the pre-written Python scripts that comes with the installation, and you can just run them. So here for the Offload Advisor run, we have two Python scripts like collect.py and analyze.py. So the collect Python script, what it does is it runs several different analysis that are supported from advisor, like survey, trip count, or dependency analysis. And once it is done, analyze script will make use of those metrics that the collect.py has created, and it models it for the target platform. So which means that I'll have to specify something called as config flag, and for that flag the parameter can be whatever the architecture that you want it to be modeled for. So in this case we have specified the config to be Gen 9, so it is going to model it for Gen 9. And if you want a different architecture, you can change this to a different name like Gen 11 or so on. So at the end of analyze.py run, you will have a HTML report generated. So and if you're not comfortable with these Python scripts, you can still go back and use our traditional advisor like C command line utility, and you can also pass on what all the different types of collections that you want to run, and you will have more control when you go to that part compared to this, because this will have some predefined set of analysis that the advisor is going to run. Okay, and yeah, so at the end you will have the HTML report generated, so which is very lightweight, and you can port it to anywhere for visualization. Okay, so I hope I am clear with what Offload Advisor is. So just to summarize, Offload Advisor is a new feature or a capability that has been added to Intel Advisor. So it helps to identify potential candidates to offload and potential performance benefits or performance speedups that you get by offloading certain sections to the GPU. Okay. Next, we will talk about roofline analysis for GPU code using Intel Advisor. So I'm not sure how many of you are aware of roofline analysis. So this is again, it's present from quite some time, and it was supported for CPU. And with the Intel oneAPI, we have added support for Intel GPU. So when I say CPU, when I say in general roofline of advisor, it means that you will get to know what is the actual performance of your application or loops with respect to the hardware limitations. So if you're running on certain machine, it has some capabilities. It has a maximum capability with respect to compute or memory. You cannot go beyond that. So at any cost, you'll be gated by that maximum compute or memory capability of that machine. So with respect to that, where you stand or where your loops stand with respect to the hardware limitations is what you get from roofline analysis. So once you run the roofline analysis, you will get a graph similar to this. So this is actually the GPU roofline analysis. The CPU roofline analysis, when you run also, it will be similar, but just that these roofs will be different. The values and the roofs will be different, right? So when I run the roofline analysis, you will have the graph wherein your x-axis will be arithmetic intensity, which is nothing but flop per byte, which means that how many operations you can do per byte of data, and your y-axis will be gigaflops or a performance. So, and here your horizontal lines will be the compute roofs, and then your diagonal, here the diagonal lines are the memory roofs. So again, these memory roofs are like different memory levels, right, in our system, like DRAM or LLC or L3, L2, L1, and so on. In case when we run GPU roofline analysis, we will see different memory rooflines, because for GPU, the memory levels are different compared to CPU, right? So it will have its own SLM, L3, and there will be a GTI interface, and then comes your DRAM. So this is what is some difference when you see when you run CPU and GPU roofline analysis. But at the end, this roofline analysis is to identify how you are performing with respect to hardware limitations. Is there any headroom for further performance improvement? What are the likely bottlenecks are going to be? is it that your application is mostly memory bound or compute bound? So these dots are nothing but the loops in your application. If you see these dots to be towards left of this graph, then they are most likely to be memory bound, and if you see them to be to the right of this graph, they're most likely to be compute bound. So you'll get to see in overall if your application is mostly memory bound or compute bound, and if you get to know that, you can decide on your next optimization strategies. If it is compute bound, you will have to think you'll have to go for some optimization strategies related to compute optimizations, and if it is memory bound, then you will have to think of some memory related optimization. So with this, you will get to know what optimization steps that I'll have to do to further improve this application. Okay, so as I said earlier, you will get to see the headroom for performance improvement. And I forgot one thing to mention here. You might be worrying what all these, like you see single line and several dots here. So recently we introduced something called as memory level roofline, which means that for a given loop, you will see at least 4 dots. So like like may not be 4 dots, but it depends on how many memory levels that we have in our system. So depending on that, whatever memory levels we have, those many dots we will see. So here in this case, I am seeing 4 dots. So one is corresponding to the GTI, which means that how much of data is being transferred between GTI or L3, and then we also have 1 dot for L3. Between L3 and DRAM, what is the data is being transferred between SLM and L1. So this corresponds to the data transfers of that particular loop for that particular memory level. When I say SLM, it is for SLM. What is the data transfer that is happening from SLM, from L3, from GTI, and so on. Okay, and once you have this roofline report, you can actually do some configuration settings. If you want to see only one memory level to be appearing on this on your report, you can configure it by selecting or unselecting these different memory levels. And as I said, it shows the performance headroom, what are going to be the likely bottlenecks of your of your corresponding loop, and you will also see the next optimization step. So once you run, you will in the bottom you will see okay, so for this particular loop, L3 bandwidth is the bottleneck. So try doing some memory-related optimizations like cache blocking. Some sort of recommendations or next steps you will get from running the roofline analysis. Okay, like Offload Advisor, GPU Roofline is also supported in GUI, and if you're a non-GUI user, you can even the command line is also supported. And to get roofline analysis, actually we will have to complete the survey trip count and flop analysis. At the end of all these analysis, we will get to see the roofline. But for the GPU roofline, you will have to include some few other flags, and make sure that you have a code running on GPU. So we will be doing GPU roofline analysis only after putting certain sections of your code onto GPU, either by using DPC++ or OpenMP, and so that it's actually that section of code is actually running on the target device, which is Intel GPU. So once you have something running on GPU and you want to see where your GPU application performance is with respect to the hardware limitations, then we can go ahead and run GPU roofline analysis. I hope I'm clear. So just to summarize again what GPU roofline analysis is for. This is to understand what is the performance of your compute kernels or the loops of a GPU application which is running on a target GPU. with respect to the hardware limitation. So you will, at the end of this roofline analysis, if you interpret the roofline report, you will understand if your application is memory bound or compute bound, or what are the limiting factors for further optimizations, and depending on this, you can strategize your next optimization steps. Okay, that was all about Advisor with respect to Offload Advisor and the GPU roof analysis. And now we will cover about VTune Profiler. What are different types of GPU analysis that are supported from VTune Profiler. You all might be aware of VTune Profiler. This is again one of the popular performance profiling tool from Intel, which helps you to understand what are the hot functions or the top time-consuming functions in your applications. What could be the microarchitectural inefficiencies in your applications, and how you can fix it. Why am I spending most of time in particular line of code? What can I do next? And all those sort of things you will get from VTune profiling, right? So now with Intel oneAPI, there are two different types of GPU analysis types that have been added. One is the GPU offload, and that is the GPU computer media hotspots. Actually, the GPU computer media hotspots analysis, it is present from quite some time, because we used to support, we had integrated GPU, and we used to support OpenCL and other stuff, and this particular analysis type was helping us those applications. So now with the oneAPI, we have added a DPC++ support to compute media hotspot analysis. So which means that you can now run a DPC++ application which is running on GPU and profile it with GPU offload or complete media hotspot analysis from VTune Profiler. So it's like now you already have GPU code. So you have identified a kernel or a loop which has to be offloaded to the GPU, and you have rewritten it using DPC++ or OpenMP, and now that the kernel is actually running on a GPU. So now we can. This is a stage where a VTune Profiler can come into picture to help you identify. Okay, you have done the offload. Is my offload efficient? Am I doing the correct offload? Or okay, it's okay now. It's the application, the kernel is running on GPU. How efficiently it is using all the GPU resources? Or are there any stalls? Are there any latency issues, or any other performance bottlenecks that are there in your application? We can find out all those details from these two types of analysis of VTune Profiler. So GPU offload is one of the GPU analysis type, which can be used to identify if your offload is efficient, or is your whatever the offload that you have done, is it a CPU bound or it's a GPU bound, and what are the top time consuming kernels that you will have to choose for optimizing next, and so on. Okay. And the computer media hotspot analysis is for identifying how efficiently your GPU kernel is being run on the target platform. Is the GPU usage fine? Are there any memory latency issues, or that will have to be addressed, and so on. So these are like two different analysis types. To start with, we recommend to use GPU offload, so that you will get to know if the offload itself is efficient or not. Once you decide that, okay, yeah, offload is good enough, and it is trying to use all the resources effectively, or so on, then we can skip on the running to compute media hotspot analysis, and see if there are any bottlenecks that can be improved with respect to memory latency issues, or inefficiencies in your algorithms. Okay, so once you run GPU offload profiling, you will again the way you get details in other VTune analysis types. Here also we get like summary and then some detailed report. So as I said earlier, the offload profiling is to identify whether your application is GPU bound or CPU bound, how efficiently your code is offloaded to the GPU, and so on. So from the summary, what you can identify is you get to see is that the GPU usage, the execution unit array stalled or idle, how much bandwidth, how much of your code is actually GPU L3 bandwidth bound or DRAM bandwidth bound, what are the hottest GPU compute kernels that are running, and so on. So if you look at this, at least in this example, GPU usage, it says only 0.6%, which means that you are not at all using all the available GPU resources or the execution units. So this is a this is something that we'll have to work on and see how we can improve the GPU utilization. And so since the GPU utilization is low, obviously the execution arrays will be stalled or idle. So why they're stalled or idle? We will have to go and explore what would be the reason that they are stalled or idle, why they're not being active all the time. So all these things that you take away from the summary page itself. So these are like some call to the next actions, what you will have to do. In addition to this, in addition to what you see from the summary page, you will also get some details on the data transfer actually. You see here the summary graphics platform and other tabs. So the previous all these details are from summary tab, and when we move to graphics, we will see some important or interesting data with respect to the data transfer. So what you see here is that for all these compute kernels that are running on GPU, it actually shows the breakup of what is the compute time and what is the data transfer time. Again, data transfer time is divided into in and out, which means in is that the data traffic from CPU to GPU, and out is from GPU back to the CPU. So you will get to know if your if your data transfer time is too much, then you will have to go and rethink why the data transfer is too much. Is there anything that you can do to minimize such data transfers? And yeah, so this is like one nice utility that that helps us to understand if you're actually doing the right offload. Are there any data transfer overhead issues? Are you spending a lot of time in data transfer, or you're spending a lot of time in compute? So at the end, our strategy is to improve the GPU utilization, improve the execution unit utilization, or minimize the stalls or idle situations, and do more compute and less data transfer. So that is what will be our optimization strategy, and this is one nice feature which will help us in identifying data transfer issues. Okay. Next, coming to media hotspot analysis. So as I said earlier, this is to identify if there are any memory latency issues or inefficiencies in your algorithm. And as I said earlier, this analysis type was present from some time, but it was supported on OpenCL and Media SDK applications, and now it is supported for DPC source and assembly code as well. So with this, you will get to see the GPU side of call stack as well, which is a very good feature. And again, this is a purely GPU bound analysis, but it will also end up collecting some other SOC related metrics. And this is one of the such platform diagram that you will get at the end of running this analysis, wherein you will see how much of data is being transferred between different memory levels, and you will also see how execution unit is being used, how much is actively being used, how much is stalled or idled, and how much of data is being transferred from L3 to L1, L2, or between LSLM to the execution units, and so on. Next, this is about the GPU architecture. This is just for your understanding, and it's genuine architecture. Just to help you understand this particular figure here, I'll just give a high-level overview of this architecture. So usually we have slices, sub-slices, and execution units in our GPU architecture. With Gen 9, we have a single slice, which in turn has 3 sub-slices. You see here 3 sub-slices, and these sub-slices will actually host the execution units, and each of these sub-slices will have 8 execution units. All of them are interconnected, and they will have their own L1 and L2 and are connected to the L3 data cache using the data port. And so each sub-slice will have their own L1, L2, and they will have access to the shared L3. And this L3 will have something like shared local memory. Within L3, you can, this is like smaller memory, which is comparatively of high speed compared to L3. And next, this LLC will be connected to the GTI. This L3 cache will be connected to the GTI, which is a graphics technology interface. And GTI is going to be connected to the LLC of Uncore. And that LLC is connected to the DRAM. So LLC is also connected. So that final LLC is shared between GPU and CPU. So that is what you will see from here. So this is the system DRAM, which is now LLC is connected to that. So this LLC is connected to it is shared by CPU as well as GPU, but it is not directly shared by GPU, but GPU will access it through GTI. So this is the GTI I was referring to. And then within GPU, these are all different memory levels that we have, which is L3. Within L3, we have smaller shared local memory. And next to that level, we will have L2, L1, and which are directly feeding to the execution units. Okay, so this architecture is just to help you to understand the platform diagram that you get from compute media hotspot analysis, just to correlate that. Okay, so some details about compute media hotspot analysis now. So again, from within compute media hotspot analysis, we have 2 different configurations that you can see from here in this picture. One is characterization and the source analysis. So once you select this compute media hotspot analysis, either you go for characterization analysis or the source analysis. So when I say characterization analysis, this is to characterize the code performance on Intel GPU. So this has many predefined presets that I'll talk about in next slides. And other one is source analysis. So this is to identify the stall reasons or basic block latency issues due to the algorithmic inefficiencies. So whenever you try to run this particular compute media hotspot analysis, you can choose either of these configurations, characterization or a source analysis. So as I said earlier, the optimization strategy here is that you will have to maximize effective execution unit utilization. You will have to maximize the SIMD utilization and minimize the stalls due to memory issues. So this should be your optimization strategy for the GPU application. Okay, so as I said, when you choose the characterization configuration, this is to characterize your the code performance on Intel GPU. So this has many presets like overview. So if you when you click on this, actually when you select the characterization configuration, so if you see here comes something like compute basic has been selected. So this is a drop down list. So when you click on that, you will get all those predefined presets. So something like overview, compute basics, compute extended, full compute, dynamic instruction count, and so on. So all these are like different presets that are intended to collect different metrics or do some different analysis with us and give you some different metrics. So based on our need, we can select any of those presets. So basically, when we select overview preset, it is mainly to analyze that particular configuration will analyze a sampler, the general memory, and cache accesses. And when I select compute basic preset, it is to track accesses to different types of GPU memory. So this is what all these predefined the presets are for. Similarly, the extended and full compute and dynamic instruction count, all these different presets are available. So based on the requirement, if you are interested in tracking the accesses to different GPU memory, you will go with compute basics. Or if you want just a high level of how the sampler is being used, how in general the memory accesses are, then we can go for overview preset. So it all depends on what you're looking for. Okay, now once you are done with or once you finish the characterization, next we can actually move to the source analysis configuration. So within again source analysis configuration, the way we had the presets for characterization, similarly we have two presets here with source analysis configuration. One is basic block latency and another is the memory latency. So basic block latency analysis, this is to identify algorithmic inefficiencies, and memory latency is to identify what are the memory access, if there are any issues related to memory accesses. So again, two presets serving different purposes from source analysis configuration. So when I say we can run any of them, and again depending on the need, if you are interested in identifying if there are any issues with the algorithm, I will be running the basic block latency configuration. So the basic block is nothing but some structured code wherein you have single entry and single exits. So VTune is going to profile only those basic blocks in this configuration. And then in case of memory latencies, you will get to see if there are any memory access issues with memory accesses, why there is a certain latency for certain operation, why it is taking a lot of time, and so on. And one more interesting thing is that you will get to see the assembly also side by side. So if you look at this picture, you have our normal the GPU, the source code, and for that corresponding we have the timing, and then we also get to see the corresponding assembly for this particular source code. So you will get to know if you're using the right set of instructions or why a particular instruction is taking a lot of time, and so on. Okay, I hope I'm clear with the GPU analysis types supported by VTune. So just to summarize, there are two types of GPU analysis that are supported by VTune. One is GPU offload analysis and the other is complete media hotspot analysis. To start with, we recommend you to run the GPU offload analysis, which to identify whether your application is whether your offload is efficient or your application is GPU bound or not, or you're using the GPU resources effectively. And then once you run that, then you can probably switch to the complete media hotspot analysis if your application is GPU bound, and analyze why your application might not be performing. Are there any reasons related to memory issues or some basic or algorithmic issues? And to explore all that, we will go for compute media hotspot analysis, which has many presets to choose from depending on the need. Okay, now we're almost at the end of our slides. To summarize, we have mainly two profiling tools as part of oneAPI, Advisor and VTune Profiler. So these two tools have added some new features of the capabilities for oneAPI. So when we talk about Intel Advisor, it has added Offload Advisor, Offload Modeling, and the GPU Roofline analysis. So I already talked about all these things. So to summarize, Offload Advisor is to identify the potential candidates and the potential performance speed up from the by running it on the target platform. And GPU roof analysis is to identify where you stand, what is your the performance with respect to the hardware limitations. And with VTune Profiler, we have two different GPU analysis types, or GPU offload and compute media hotspots. So these two analysis types will help you understand if your offload is efficient, or if you have any issues with your algorithm, or if there are any issues with the memory accesses, so that you can strategize your next optimization steps and go on. Okay, so at the end, we have provided some resources and for you to go and dig deeper. So we have we have added some links to download. The oneAPI based toolkit, or you can also download the standalone version of VTune and Advisor, and you can start profiling your tools. And if you get into any issues, please write back to us, and we will help you with your issues. So that's all I have for today.